It's preparing to live stream the meeting. That looks good. So, yeah, I think we are live. Hi, hello. Welcome to Christiaan Baaij's talk. I nearly messed up the name. I probably still have messed up the name. I don't know. He's one of the co-founders of QBA Logic, where they do FPGA design and development, and where they have successfully started the open source project Clash. And I think in his workshop here about RISC-V system on a chip programming, he might probably mention that. And I would say he cannot start and have fun giving your talk. And I will monitor questions and will monitor the chat. So have fun.
Thanks, Maximilian. I'll share my my screen.
Screen sharing is working?
Yep. Okay, very good. All right. Welcome, everyone, to this tutorial / workshop on designing a RISC-V CPU in Haskell, and then integrating it into a larger system, which will be done in Python. This is the alpha version of the tutorial run, so I apologize for that in advance. I had great ideas for this, but whilst working on it, I realized that, doing exercises and things perhaps within 2.5 hours is almost undoable. So what I'll mostly be doing is going to be a live coding session, which you can follow along. If you've installed the tools, I posted them on the Slack channel a couple of days earlier, so you should be fine. If you already checked out the Contronomy Git repo, then all you have to do is do a new git fetch and go to the tutorial branch. Otherwise, whilst I'm talking, I'll leave this this website a bit open so people can follow along. Right, this tutorial workshop session will be a 2-session part. Halfway through, we'll have a half-hour break.
Just a minor interruption. Can you slightly increase the font size?
Of the website?
Of both sides.
Yeah.
Perfect. And the comment was slightly is not enough. Maybe a little bit more. Yeah, that looks at least very readable for me.
Okay. Yeah, I will be switching to full screen. Let me just switch this to full screen. Yeah. So yeah, another thing, as you can see, I'm full screen on either this website or the or on my code. So I won't be able to read the chat because I have a single monitor setup. But Max will notify me if there's any questions, like he has been doing so far. Really good. Right. So a bit about Clash. Clash is a compiler for Haskell, which takes a semantic subset of the language and translates that to hardware description languages, which the downstream tools understand and comprehend. So what do I mean by downstream tools? So like I said, Clash produces hardware description language source from original Haskell. And these hardware description languages are called Verilog or VHDL. And they are, let's say, they can be used for high-level design, but we're using them as a sort of low-level description, let's say the assembly equivalent of hardware. And we can then use, from this Verilog code or VHDL code, we can create actual ICs, usually called ASICs, application-specific integrated circuits, using tools that are out there. So they convert this Verilog to basically, let's say, a very fancy SVG, which the wafer steppers understand and can turn into an actual IC. But what we'll be doing here today, or we'll be showing at the end of the workshop, is that we can program a FPGA, which stands for Field Programmable Gate Array, which is a highly specialized chip, which can be reconfigured to do any kind of circuit. And the way it works basically is that internally they have such a chip has like millions of lookup tables by which you can implement arbitrary functions, and also has, lots and lots of routers between them to connect all of these lookup tables. So you can sort of, it's basically that you're putting the circuit on a reconfigurable chip. I have one here. Let me switch to my OBS feed so you can see it. So this is the FPGA that we'll be running on at the end of the day. Switch back to the website. So yeah, the FPGA will run our RISC-V CPU, which is integrated into a larger system on chip, which will give it SDRAM, a UART to communicate, so we can actually see what's going on inside of the chip. Okay. If you haven't, haven't been able to follow along completely, the link to this slide is in the Slack channel, so you can keep on going with the instructions from there. So let me switch to my editor. So I'm here in the Contronomy tutorial. Contronomy is the name that I gave to the RISC-V core that we're building. The reason for this name is that paradox.com is not available, and neither is Antinomy. So I took a different version of anti, and I took the Latin contra. So that's why we've ended up with Contronomy. Anyways, that's if you're wondering why it's called that, that's the reason. So, like I said, Clash takes a semantic subset of Haskell, but it's not regular Haskell. It takes GHCi Haskell. So we will, so the Contronomy repo contains a Cabal project, but it works with Stack as well. And it defines all the common options which are normally enabled by the Clash compiler. And as you can see, it's, let's say, GHC kitchen sink. And that's because we use some of the, let's say, dependent type-esque features of GHC for circuit design. But, we will use normal GHCi. Then additionally, we've improved the solver a bit to give you a bit more reasoning about numbers at the type level, because in hardware we will be dealing with fixed sizes. Like we need to know how many bits something takes. So for example, we need to know if we don't work with lists, but we work with fixed size vectors. So lists that have their length annotated at the type level. And so for, working with these type level numbers more straightforwardly, we also need to enable some plugins. Clash is a whole program compiler for Haskell. So we, as some of you might know, GHC's underlying representation for Haskell is core. And this is like a mini Haskell. And so if we compile anything, and if we want to reuse stuff we develop in one project and use it in another project, we need to make sure that this core is stored in the HI Haskell interface files that GHC creates. So that's why we need this fexpose all unfoldings. And then here's a very long story, which I can discuss over a beer, although it's kind of early for that. Luckily, I have alcohol-free beer in the fridge, so I could have a beer if I wanted to. But yeah, that's a long story why we need this special thing. So let's get to it. We will start with version V0 of the core. So let's switch to the directory. I'm a Cabal user, but I think if you use stack, it will work as well. If not, you should have joined a bit earlier the Slack channel, because then I could have helped you. So we've loaded our design inside the REPL. As you can see, it's loaded. Let's go to the source and open up core. This has some inputs, some additional language extensions that we'll be using. Here's some imports. And these are some things I will discuss later. So what we'll be building is a non-pipelined CPU. So it doesn't even, so that means that it will take multiple clock cycles to process one instruction. That's because it's just easier to describe in such a workshop, and also it's much easier to design. We will, so that's it for the CPU as a general concept. We will be implementing the RISC-V base integer instruction set. If you go to riscv.org and then go to specifications, you can download these two PDFs, and they specify the RISC-V instruction set. This is the PDF with the so-called unprivileged set, which is, let's say, the normal instructions that don't have anything to do with like memory protection. If you think about operating systems where you have like user mode and supervisor mode and machine mode, those parts are described in the privileged set, and this part describes the base instruction set, and here describes like that we have registers that we can, so the RISC-V is a register machine. It describes the format of the instructions, like the bit encodings, what kind of operations that we have on integers, whether we have immediate instructions, which means that they work on a value encoded inside of the opcode, all kinds of other instructions. They're all described here. And yeah, we will follow this spec along. So the CPU will need to communicate with the outside world. And the way it does that, is over, in our case, over a so-called Wishbone bus. So yeah, Wishbone is as you see here, is a standard on how components can communicate inside of a system on chip. Yeah, it specifies like an interface and a protocol to which you should adhere for things to work correctly. Whilst designing this tutorial, I violated the protocol many times, and it does result in very weird failures. But anyways, it will probably be easier if I just show you the Haskell code that corresponds to this interface. So the Wishbone interface is a two-way communication channel. You have a thing called the Wishbone master, which initiates transactions on the bus. And then you have a Wishbone slave, which responds to transactions on the bus. On this, if it's called a bus, but it's really a what you implement is really two unidirectional signals. There's no, for those that are know a bit about hardware, it's not a multi-master bus on a single wires. So the Wishbone bus is, like I said, it's a standard for communication between peripherals on a system on chip. And so a system on chip is like a combination of circuits that together they form a whole, and they need to agree on how to communicate with each other, and we will be using the Wishbone protocol. So the Wishbone protocol has like an address. So it's a so-called memory mapped interface. That means that you specify an address where you want to receive data from, or want to write data to. So that's what we have here. And here we can see right away something that's class specific. So we have a bit vector, which is an n-bit data type. So encoded at the type level, we say how many bits do we want, and so that's because we need to know how large things are. I'll explain this part in a bit, but here we can see that we have a bit vector. So that's the address. So we have an address of address width, then we have the data, and here MOSI stands for master out slave in. So this is the data that we want to communicate from the master to the slave. Then we have the bus select. That specifies which bytes that are present on this write data are valid. Then we have something called the bus cycle that just specifies that there's currently a transaction going on. On top of that, we also have something called the strobe. This indicates that so the bus cycle sort of indicates we are writing something, and so there's currently a transaction going on, and that's controlled by the master. But then the strobe indicates that the master actually changed the values that are now present on write data, address, and bus select are now valid. Same for write enable. These two things will not cover for today. So this is the interface so these are the values that we need to define in our Haskell specification to communicate to the outside world to get our instructions for the CPU, but also to read and write data from the memory, which could be like a ROM or a RAM or even SD-RAM that we'll have on this FPGA. So we'll communicate over this bus. And on so what the slave sends, or what if we have the responder, so this is what we as the CPU will get back, is the read data. So that will be the data that's specified at this address. We'll get an acknowledge, and this will become true. So the slave will make this value true once this read data is valid. Now, there's also an error signal, and the error signal, it indicates that we've been trying to access an address that's not there, or something else is going on, because our reads and writes, they might be side effecting, which means that if you read from an address, something might change, or if you write something to an address, something might change, and it might not be in a correct state to do that. In that case, the slave should raise an error, and we will handle that as well in our CPU. So this is the interface that we'll be communicating over. So now,
just
yes?
a short question from the chat.
Mm-hmm.
So there's someone saying that the LiteX setup pi space install command fails with an error. Maybe you can have a look at that.
Yes, I will help out during the break when we're gonna debug live.
Good. Please continue.
Yeah, perhaps somebody else in chat can help out. Right. So how are we gonna create our CPU? So we are going to write a so-called Mealy machine, and a Mealy machine is like a standard model for circuits. And the way it operates is so.
Hi, I have a question about Wishbone before we move on.
Yes.
Suppose that I want to read from a memory address and the peripheral that's backing that address is not yet ready. Like maybe it's RAM that has something else reading from it, or maybe it's asynchronous RAM that requires several cycles to get an answer back to me.
Mm-hmm.
In that case, so what's the Wishbone story for this? So for example, does it latch the address until the memory becomes ready to serve me, or does the CPU have to do that? Does it include some kind of address in the result to tell the CPU that this is the read result for this particular read request? How does that?
Yeah, so we will be operating in Wishbone Classic mode. If you read, you can read this spec and see what that means. So in terms of the protocol, what it means is that once we assert strobe, so once we make strobe high, we are no longer allowed to change address, write data, bus select, or write enable. These need to remain the same value until and including the cycle that the bus indicates acknowledge. So the slave. So yeah. So we can't change these values: address, write data, bus select, and write enable, and also not bus cycle, until the slave either trigger sends us an acknowledge, or until it signals an error. There's another version of Wishbone, the non-classic version, which works slightly differently, but we'll not be discussing it during this workshop. Does that answer your question?
Totally, yes, thanks.
Okay. So coming back, so we will describe a Mealy machine. So a Mealy machine basically is a function that goes from the current state and the current input and produces the state for the next clock cycle and produces the current output. So this is how we will, how we were going to define our CPU core. Now there's already some stuff here set up, which due to time constraints and can't, I will discuss whilst I implement them, but I can't discuss them up front because due to lack of time. So how are we going to start? So in this case, so we have our core state and we are in the instruction fetch state. We have our current program counter. We have the response on the instruction bus. So this is the Wishbone instruction. This is the bus corresponding to our instructions. And this is the response channel for that bus. And now we have to update our state. We're going to use the state monad for that. This is basically run state, but for those familiar, this is basically run state, but with its arguments flipped. So yeah, what are we going to do? So we are first, so the core state contains the stage that we're in. We're either fetching an instruction or executing instruction. It contains the program counter, so where we're currently at. And it will also contain the instruction that we fetched, because we need to remember that as we go to the instruction stage. So I'll be using generic lens for this case to update the instruction field. So we get our instruction is going to be the read data that we get from the bus. Right. And what we need to do, so now so we've gotten the instruction that will be stored for the next state. Now, when can we move to the next state? Well, that we can move to the next state once the slave side of the instruction bus has acknowledged or raised an error. So our next stage is going to be, well, let's handle the default case first. So if we get an acknowledge from the bus, then we go to the execute state. Now the execute state also records whether there was a fault. So there was no fault in this case in accessing the instruction at this address. Otherwise, if there was an error on the bus, then we also go to the execution state where we go to we do false. Now you might be wondering, like, why don't I go back to the previous this instruction fetch stage again and maybe erase the program counter? Well, that's because later on we'll actually be handling these kind of exceptions in the execute state. So that's, in this case, we indicate that execute is false, and otherwise, well, we stay in the instruction fetch stage. Right. So the core output. So we have two buses: the instruction bus and the data bus. So we also need to update our instruction bus, the master side. So this is going to be the output. We're gonna take a default value for the Wishbone interface, so we don't have to think about all the fields that we don't care about. So we're gonna take the default a default implementation. Now we want to get the value at the current program counter. We want to get all 4 bytes. Or let's just be more explicit. We want to get all 4 bytes. And we want to, so we're going to start this, we are doing an active cycle. And we're not going to change any of these values until we've received an acknowledge or an error. We don't care really yet about these arguments. So at this stage, we have, we're we're communicating over the bus, telling we want the instruction that's at the current program counter. We want all of the bits, because we'll come back to this bus select later. But for this bus, we always want all of the bytes. We started the cycle. All of our values that we're interested. We're not writing anything, so we only do the address. So that's it for stage 1. And next up, we'll go to the write back. We will go to the execution stage. We're gonna now change to version 1. Load up. Okay, so we have so we've been able to fetch now instructions from the bus, but of course, we also need to execute them. And so we're gonna move on now to the first part of the let's say the base instruction set. Those are the load upper immediate. That's basically, so there, in this case, the instruction will contain a value that we need to load into a register. We can load an address at an certain offset from the current program counter, and we can do some operations like add, shift, compare, exclusive OR, another shift right in this case, ORs and ANDs. Yeah. So if we go to the spec, we can see here that these simple register-to-register operations, they store their bits, the register operands at these particular fields, and we need to make sure that they are fetched from the register file. Okay, so what is a register file? If you go here to register file, we open it up. I'm not going to explain this in too much detail, but a register file is basically a small piece of memory that we can read and write from, and write to. In this case, we always want to read 2 addresses, A and B, and sometimes we want to write as well. Also, we of course want to get these values back, but in this case, for this implementation of the register files, we have to be careful that we won't get the value of address A until 1 cycle later. This works out so that so knowing this, I am going to fetch the operands already in the instruction fetch cycle. So we have a function called decode instruction, and it helps us. If we go here to decode instructions, so decode instruction basically fills up this struct, And it contains all kinds of relevant fields for particular operations. We won't be using all the fields all the time. But from the 32 bits that are specified here, it takes the relevant fields for all of the operations that we will be doing. So yeah, you're not always interested in all of the fields. So in this case, for the instruction decode, we are for the instruction fetch states, because we want to get already the values of these two registers. We call here decode instruction. We get these two the values of RS1 and RS2. And we provide them here on the output.
We have a question by Georg. Maybe you want to ask it, or maybe it's George, I don't know.
Well, yeah, I mean, my question was just that, did I see that right? That the register file implements the access to two registers at a time by just copying everything into two block RAM?
That's right. That's because the base library for Clash lacks a RAM primitive with more than
sure, but at that point,
two primitives.
So these are tiny, right? These are like 32 registers, or how many registers are there?
Yeah, 32.
Yeah, so couldn't you use 32 registers? I mean, Clash registers?
Yes, probably. But
I guess my question is just like, when would you pick one or the other? Like for such a small handful of registers, I would have tried just having a vector of registers.
Yeah, like I'm using block RAM here, which is a a RAM primitive that you find on many FPGAs that have a 1 cycle delay on their read ports. But I probably should have used the so-called, in Clash we also have an async RAM, which would correspond to the smaller RAMs that we have on FPGAs. Those would have probably been better suited. But I guess I could have also implemented them directly in registers. But yeah, there would have been many options to implement this this particular register file. Yeah, the block RAM, yeah, it's supposed to be actually, so for this tutorial, we don't really care about the instruction, the implementation details of the register file. But yeah, there are different options of implementing them, including what you said, Gergo.
I was hoping that you would say that, oh, but this is much more efficient in terms of parts used or something along those lines, because
well, the async RAM would definitely be, because it's still, yeah, like the asynchronous RAMs that you have on the FPGA, it would definitely be more preferable, because that would fit into one almost, or perhaps two logic slices. Actually 4 maybe, because it's 32 bits wide. So yeah, this is more, so this is wasteful because I've used block RAM, but if I used another type of RAM, it would have been less wasteful than using individual registers. Okay, we're getting back. So we've gotten the addresses for the registers. And we now, because the register file does not live, okay, let me just finish my sentence first. So we've gotten the addresses, and we now output the addresses here in our return field. So these addresses will be sent over to the register file. You might be wondering, like, oh, but Christiaan, why didn't you just call register file inside of transition? Well, that's because transition is a pure function. Actually, in Clash, they're all pure functions, but in this case, let's say transition works at the single cycle level. You know, this is a normal Haskell data type. If we look at register file, however, it operates on signals, and signals are just infinite streams of values, and we use them in Clash to represent sequential circuits, so circuits that operate over time. So it's a circuit operating on a stream or a signal of values describes a so-called sequential circuit. So the types simply won't match up. So here we have something that operates on infinite streams to implement sequential circuits. And inside of transition here, we have a combinational circuits, and we can't just mix and match them inside. So that's why we just send over the addresses, which we will then get back here during the execution stage. So now we move on to the execution stage. But this will be one cycle later, right? Because transition just describes what happens at every clock cycle. So we will be one cycle or even more, depending how long it takes for the bus to respond, or at least multiple cycles later, until we've reached this execution stage. So, and here, so we get the two values from address RS1 and RS2, which we then feed into our ALU. So the ALU will take the ALU will perform, as I said, multiple instructions from the RISC-V instruction set: load up immediate, address and an offset from the program counter, and these operations. So we pass in the instructions. So because it needs to calculate an offset from the program counter, we also pass in the program counter, and the two values from the registers. So we also need to write to the register file. If we go here, we can see that the opcode declares the destination address. But we shouldn't be writing to the register file for all operations. So we know the ALU implements the standard op, register to register operations, the immediate operations on immediates, but again, they are values encoded. They have values, constants encoded inside of the instruction that the ALU handles, the load upper immediate and offset from a PC. But in all other cases, the value that we want to write to the register is basically nothing. In addition, if this is according to spec, if the destination register is 0 or x0, then we don't write anything either. And then here we use the applicative on the functor on maybe to combine these two values into a pair of address and value, but wrapped inside of a maybe. And then if we here scroll down, so this register write file, the register write value is the value that we'll be writing to the register, but it's potentially nothing in case we didn't want to update the register file. So yeah, again, we use our function decode instruction to get the to get the opcode and the destination address. I'll get to the implementation of the ALU later. So basically, the ALU can operate instantaneously. So on the next cycle, we want to fetch the next program, the instruction at the next address. So we just increment the program counter by 1. And we go back to the instruction fetch stage. Now, some of you already commented on chat that the test suite is broken, as in it's not really implemented. And that's because I've been using the did I forget it? Right, I didn't. I've been using the RISC-V formal verification framework to verify that the Verilog generated byclash from our specification, or from our, corresponds to this formal framework. So this tool uses bounded model checking to verify that the CPU behaves according to spec. So that's what I'm not going to go into too much detail here, but that's why we have this RVFI out to indicate that, so this collects all kinds of information from the state of our CPU, outputs it in this expected format, which the formal tool will interpret and then tell us whether we were executing all of the instructions correctly. So that's what we are collecting here, and that's what we're here producing here as an additional output. As you can see, I'm checking the time all the time because I don't think, as I said, this is the alpha version of this workshop. And I don't think I'll be able to live code everything. So I will do the ALU right now, but I'll probably skip over some of the other parts.
There was a short question if RVFI is like the debug output of the internal state.
In a way, yes, but it is then also, again, implementation agnostic, right? So multiple implementations of the RISC-V should output the same same value. But yeah, you basically, I can quickly go there. So you basically tell it what's the address for RS1 that you decoded, what's the address for RS2 that you have decoded, what's the value of RS1, what's the value of RS2, what's the address that you decoded, what's the value that you want to write to this address, what's the current instruction, or what's the current program counter, what's going to be the next program counter. So yes, in a way, this is it encodes the internal state. Also, we have a valid flag, so the formal tool only checks the output once you've asserted valid. So yeah, you basically output like a trace of your entire CPU, and the formal verification tool just checks that using bounded model checking, that all traces are correct.
Thank you.
And this was actually ideal that I could use this format, because there's lots of small little details in the RISC-V spec. And so yeah, I could have written my own test bench and done quick check perhaps, but I think for this particular case, the bounded model checking is a lot more, it's bounded in terms of the number of cycles that it checks, but otherwise it's like it's exhaustive. So it's really good in that sense that, so yeah, you also need to tell it for how many cycles it needs to at least run to get a proper trace. That's the problem with bounded model checking. But for our configuration, we've given it enough cycles to make sure that our traces are long enough to verify formally. Okay, so we now have to implement our ALU. So we have to, specify the ALU result. So how are we going to do that? So we're going to so we're going to get the relevant field from the instructions, which are, well, definitely the opcode, like what are we doing? So, but the ALU, so going quickly here to the instruction format, they're like, we have operations, but operations on immediate. We have load upper immediate, offset from PC. But the ALU will perform, let's say, arithmetic. So which arithmetic, not only arithmetic, which operations do we have? Well, we have addition, shift left logical, less than unsigned, XOR, shift right, which will come in logic and arithmetic form, bitwise OR and bitwise AND. So these are the operations that the ALU needs to be able to perform. So, and then if we look at our decode field, that's stored in this IOP field. So we will need to get the IOP from there as well. Okay, so the ALU operation that we are going to do is dependent on the opcode. So if it's op, then it's simply the IOP field. If it's operation on immediate, then it's also this IOP field. And in all other cases, so in both load upper immediate and offset from PC, we will simply be forming addition, and we will be adding zeros. Hopefully I didn't make any mistakes. I didn't. That's good. So then the operations operate on 2 arguments. So what's the first argument? Well, that sort of depends on what operations we're doing. Again, this depends on the opcode. So if it's a normal operation, then it's simply the value that we get from register RS1. The same for immediate. If it's if we're doing an offset from the PC, then we need to get the PC value. But know that the PC value is a 32-bit value, but machine word is a 32-bit value. So we're going to take the PC and using, so this is, let's say, bitwise concat. So this takes a bit vector, another bit vector, and produces a larger bit vector. So we need to extend to the right with the value 0. We can be explicit. Right. So then we have the load upper immediate. And I would have to look at the spec because I forgot. Right, so the load upper immediate value is stored the upper 20 bits inside of the instruction, and so we need to fill up the rest with zeros. So also we begin to, so this is the immediate field corresponding to load upper immediate. So we need to get that from our instruction as well. And here we just use 0 of bit vector 12. Yeah. But that, what do we do in the other cases? Well, as you see, like actually it's only these 2 that are special. And so what we're going to do is going to just make the fall through case RS1. And so the second argument, that's going to be different. So if it's OP, a normal register to register operation, then it is going to be the value that we're going to read from RS2. If it's immediate value, however, no, I didn't want to. Immediate, where are you? Right, if it's an immediate value, then we need to extract this upper 12 bits and need to sign extend it to the full 32 bits. So we need to get the 12 bits corresponding for the immediates. And we need to sign extended. Oh, Yeah. Okay. So AUI PC. So again, so it takes the program counter and then also this immediate field as the second argument. So here again, we're going to add this immediate and make sure it's big enough. Load upper immediate. Well, that doesn't actually matter, so we're just going to add 0. And yeah, I think that's it. I think to be on the safe side, though, we're just going to add 0 because that's going to be a no op. And actually coming back to my original decision, as you can read here in the specification, no op is usually implemented as an add of x0, x0, and 0. So this is the destination, this is the first argument, this is the second argument. So let's just implement that for ALU. So let's go back. So OP reads RS value 1 and OP immediate also RS1 value. And then the default value is then just 0. So that should be it. So we've got our arguments, and now we can finally start calculating the result. So the result will be let me see which ones we have. Right. Addition is not as simple as you might think it is, because we can also do subtraction. Well, as you can see, the way that's encoded is that we have an additional number of bits here on the upper side, on the most significant side. And then if this value is a 1, then we're doing subtraction. Again, we store this, so our decode function extracts this bit, and it will indicate whether we have to do a subtraction. So this add operation does both addition and subtraction. So we're going to take our first argument, we're going to add, but if it's subtraction, we need to, if it's subtraction, then we negate the second argument. Otherwise, we're just doing normal addition. Right. So then we have shift left logical, or basically shift left. Here we just use shift left from data.bits. So we take ALU arg1 and we shift by ALU arg2. Now I sort of have to, I'm going to cheat because I forgot whether I need to do something special with ALU arg. Oh, okay, right. So we don't need as many bits. So this is a 32-bit number. This is a 32-bit number, so we don't need to shift by 2 to the power 32. Instead, we're just going to take the first 5 bits. So slice takes a bit slice. So we're going to take from bit 4 down to bit 0, so the lower 5 bits. Yeah, and here I'm 0 extending. So the downstream FPGA tools will optimize this away again. I guess this is sort of like a premature optimization. This is the downside of using Haskell's data.bits, because it expects an int here instead of something smaller. So this is just to conform to Haskell's data.bits. So we're going to shift by the shift amount. So set less than 0, that works on signed values. And we then, so we need to compare signed values. So the way we do that is we're going to call unpack, and unpack takes a bit vector and converts it into any data type that has the same number of bits. So we are going to unpack ALU into a signed number. Then we're going to compare. In this case, because we can infer, we can just do unpack ALU arg2. But this gives us a Boolean, and we need to convert to a machine word again. So I've added a function here inside of this contronomy clash extra, which converts a bool to a bit vector. So we call that. So we call bool to bit vector, and we're done. Set less than unsigned. We can just implement. We can just directly compare ALU arg1 to ALU arg2. That's because bit vectors behave like unsigned numbers. Well, XOR, again, we can use XOR from Haskell's data.bits. Let's skip SR. So, well, or the same. Use bitwise OR from and bitwise AND from LU. So shift, we can have 2 shifts, shift rights. We can either have a arithmetic shift or a logical shift. An arithmetic sign extends the most significant, or keeps the most significant bit as it shifts to the right. And again, it uses this bit in the upper 7 bits of the instruction to encode whether we're doing a arithmetic shift or a logical shift, which again we get from our decoder. So so that's the SR shift right, logical or arithmetic. So if it's a logical shift, then we can just use the shift right from bit vector itself, because that performs logical shift right. But if it's an arithmetic shift, then we do ALU arg1. We again unpack that, so we convert it basically to a signed number, and then we shift by the shift amount. And apparently I did something wrong. Yes. So I've converted here to assigned, and of course this is going to be assigned as well. So now I need to convert back to the machine word. So I need to call pack, and pack takes any type of the that has an instance of bit pack and turns into a bit vector of the equivalent size. Right. I did something wrong here as well, because it's not the entire thing that needs to be 12 bits. It's just this 0 needs to be 12 bits. And again, of course, this could just be inferred, so I could leave it out. Wouldn't have made a mistake, but let's say for documentation purposes, it's probably nicer to indicate how many bits you need over there.
Okay, I think with your plan for a break,
Yes.
it would be time right now. We would have one question directly before the break by Georger. I'm not sure if I'm now better in pronouncing his name or not, but maybe you can ask your question.
Sure. So my question was, so you pass these extra booleans from the decoder that tell you whether it's an addition or a subtraction, or whether it's a logical shift right or a arithmetic shift right. So why not fold these into the ALU up enum? So basically, couldn't the decoder do just a bit more work, but then the ALU would be given the the actual intention of the operation instead of the representation that happens to come from the ISA?
Yes, I agree. I think like I probably should have encoded so the way I the reason why I did it like this is because there are exactly 8 operations here, and they fit into the 3 bits that the that we have, basically.
But then you have 2 more bits for whether it's subtraction or whether it's arithmetic shift.
Right, but they're encoded in a different position. And yes, I guess I could have so again, this is more like this is going to like this would be an optimized. Like if I would give it more bits, I guess I could have done that. But then, yeah. Yeah, perhaps it would have made more sense to encode them differently than I have now. Again, this is the, let's say, alpha version of the tutorial.
But then on Slack, Luca commented on my question that maybe this way we only get one adder, because you just have a negation before it and you multiplex either arg2 or the negation of arg2, whereas if you had a different enum constructor for subtraction, then we would end up with two adders. Is that true? Is that
yes, we'll basically now only get like sometimes Clash will try to share operations between different alternatives from a case. So it might have shared the adder if we would have had a sub, and we would have done. But it's very unlikely because plus and minus are encoded as different. So you would already have to have encoded it as negate ALU arg to be more sure that Clash would have shared or would have generated HDL that would have shared the plus, because minus would be a different primitive operation. So yeah, in this case, we would be, by encoding it like this, we do get the we do get a single adder. What would have been perhaps nicer if instead of having this is sub be a field that we get from encode instruction, it would have been nice if maybe it would have been a sum of product, because the is sub basically only makes sense for the add, so it should have gone there with the add. But yes, it's now time for a break. I think I would like a 15-minute break.
Okay.
So that means we'll be back at 40 past the hour for whatever time zone you're in.
Perfect. And we had one or two questions in the chat with setup problems. Maybe they can ask, ping or mention their questions again, and we can. Maybe there's can be some help done, something like that. I don't know.
Okay.
Yeah.
Should I stop sharing or?
Please continue sharing.
Yes.
Or if I don't think that the chat is private, but yeah. Okay. Break time until 40 past. I can't stop streaming in that time, but yeah. I will also notify in the Slack chat when it is ready to continue.
Okay. Mm.
Okay, I'm not finding any other messages or any other questions. So
No, yeah, I hope I've answered.
yeah. So see you in a bit.
Mm-hmm.
regarding the name Contronomy, there was the question in the chat how this name was chosen. It was your explanation at the start was pretty fast, and also the clashes that you mentioned and the alternatives. I wasn't able to follow it, and it would be interesting to.
Yeah, it's I think the where it came from is like basically with Clash you're sort of doing things that, well, it's not really a paradox, it's just you're doing stuff you're perhaps not expecting, you know, building hardware with Haskell, which people, you know, don't really associate with close to the metal. So yeah, and I wanted to register a URL or a long time ago, but you can't take paradox.com, right? So then the closest that you have in the English language to paradox is antinomy. That one is also taken. So there's a different Latin version of anti, the anti and antinomy, antinomy, and that's contra. So I still need, so I want to put up this tutorial eventually on the URL that I originally registered, which is contronomy.com. So yes, a very far-fetched name, but basically it's the closest you could get to paradox.com.
Okay, now I understand it. I think we are ready to start again.
Okay.
Maybe we can start with a question from the chat.
Yes,
there
definitely.
was this question what the quality is that Clash produces, whether it's closer to a research tool or whether it's production ready.
It is production ready. It is used in production, not just at QBlogic, but also at many other companies. I can't name them, but there's a trader in Australia that uses Clash for their FPGA-based trading, and a large contributor to Clash is a company called Myrtle.ai, and they use Clash for all of their AI inference acceleration. Yeah, if you go to their website, Myrtle.ai, you can see the projects that are listed there, and they're all built using Clash. So the output of Clash is good as long as the input is good. Clash is not so-called high-level synthesis, where it takes a, let's say, behavioral description of the circuit that you have in mind, and then performs all kinds of transformations like pipelining and scheduling to give you a good, fast-running circuit. It's so in Clash you have direct control over, how much hardware is generated, where the registers are placed. So if you need the speed, you can get it. But this is a double-edged sword, because if you don't do it, then you will get a circuit that uses a lot of resources or has a low clock frequency. I hope that answers the question.
I think that answers the question, yeah. Okay, so please continue.
Right. So we have an hour and 15 minutes left for this workshop. As you can see, I only got to version 1 of the core. And I think, yeah, what I wanted to discuss is some of the things that I did to get the Verilog out of Clash in such a way that it can be used by the other tools. Then I will show the other tools. I think the most important bit, because as people have already noticed, there's no real test bench. I will show how we can formally verify. This takes like, it's probably a 15-minute build, so I'll run it in the background later, and then continue and then show you the results. But I'll show you how I've tested this design. And then I'll go also to the Python part and see how we can integrate it. Okay, so we can go back to our, if you're following along, just change this back to source. Just to make sure that everything compiles. It should be fine. So let's open source and open Contronomy. So here we see, now I'll finally get to this triple colon thing. So the triple colon is just is the type alias actually, and this is just a type level string. So this is the real honest to goodness type basically, and this is just merely an annotation. And we use this to name to make sure that the input and output ports, all of the ports in our generated Verilog, are what we want it to be. So we do that using this. This is a template Haskell thing. So we call make top entity. We give it the name of the thing that we want to generate Verilog for. So call make top entity, and it will use these annotations to generate the correct port names. And so here we have this core in, which was defined here. And here you can see again that we're using these names again. And if you give it a name like this, then in the generated Verilog, we'll get a separate port for this data type. Otherwise, you get like a compound port, let's say, of all the bits shifted together, and will be a very wide port. But if you give it a name like this, then let me close all that. So if you give it a name like this, you'll get a separate output or input. And then this works nested, right? Because here's this Wishbone thing that we saw earlier. You can see that we use the same annotations. So that makes sure that we get proper naming. So let me exit it. You don't need to install the Clash compiler because most of it is basically as a library, and we use it as a library inside of this project. If you scroll down in Clash, you can see that we just specify an executable, which is like barely nothing. Like it gets the arguments and passes it to the default main. So so that's why we can do cabal run Clash. So let me just make sure. So there's no Verilog in here. So if you're using stack, you can use stack instead of cabal. You can do cabal run Clash, and then you do minus. So that means the arguments that we want to pass to this class executable, not the arguments that we want to pass on to Cabal. We say we want to generate Verilog, and then we need to tell it in which module it should look. So we can do, so it should look in the contronomy module. So it will build the library. This is just regular Cabal. Yeah, now it's building the compiler. Now it Clash, behaves like GHCi. It loads the package environment, the package database, and does all kinds of type checking. As you can see here. Now the Clash part starts. It generates 2 versions of the core, one with the special output for the formal verification, and one that we'll use to integrate into the SoC builder, LiteX. So if we now look at the generated core, here we can see that, we got all of these, the addresses as we specified them here, or nested, because here we said I. So it uses the nesting as well. So here we said iBus Wishbone, and then here the names. And if we then look here, we see iBus Wishbone _ address, obviously things like that. So that's how we control the port naming. And if you don't do that, like I said, you'll still get Verilog, but if we hadn't annotated it, then we would have basically gotten one output, which was all of these bits wide, basically. So that's why you need to do this naming to make it easier later on to connect. So yeah, that's part of the naming. There is a bug currently in Clash, and that it has recompilation avoidance, but it only does it apparently well if it has access to the source, not if it uses precompiled versions. So if you're running this tutorial later and you've changed some things, currently there's 2 options. You can either say, well, just get it from the source instead of, but then, and otherwise, for now, I would say you would run with a no cache option. And that will, as we'll see later in the output, Clash will notify us that it's ignoring the cache and it's rerunning. Yeah, as you can, it's ignoring .manifest files, but that's basically saying it's not using the cache for the generated HDL. So yeah, so if you want to control the output naming or all the port naming, you have to use this, let's say, annotation. And again, it doesn't influence type checking because this triple colon operator is a type synonym. Okay. So another thing that I wanted to highlight before moving on. So we've been using regular Haskell data types like maybe, and they are all translated properly to Verilog. So that all works. In the case of this RISC-V instruction set, it's a 32-bit wide instruction, but there's many options which aren't legal, or they have a very specific encoding. But you can tell Clash to use a specific encoding, bit encoding, for your data type, I'll try to find a nice one, right? So yes, so this is the load store with data type. It's used by the load store unit, and a load store means loading a value from data memory and putting it into the register, or taking a value from a register and storing it at a particular address. And you can store bytes, half words, i.e. 16 bits, or 32-bit words. Then, like normally in Haskell, you'd be done, right? You only care, and then you can have signed or unsigned bytes. So ignoring that for now, we can say how at the bit level this data type is encoded. And so, there's special, the special incantations. If you just copy paste it from these examples, you should be fine. So what we're saying here, okay, so we're annotating the module, and Clash will pick this up. We're telling like, oh, there's a new, we don't want Clash to infer a representation for this data type. We're going to annotate one. Then we're going to tell Clash, so which type? So we do this set of template Haskell stuff anyway. So here we're saying like, we're annotating, we want to give a annotation to the load store with data type. Then we say it's going to be, we're going to need 3 bits, and then we're going to encode the individual constructors. So we're going to give a representation for the constructor byte. The bits encoding this byte constructor will be in the lower 2 bits. So here we say 1 down to 0. Then we're going to tell the value. So basically this encodes a mask where the constructor bits are stored. So we're masking in the bits 1 down to 0. Then we're going to tell it the value. So that's value 0. And then we're going to say, what's the mask for the fields, i.e. where are we going to store the fields? And here we say that we're storing the field bit, so this sign, in the most significant bit. The same for half. We just pick a different value. Again, we store the sign bit in the most significant position. And then word, that uses all 3 bits, and it's encoded as 2, the value 2, and it doesn't take any sign bits. So since we're taking in this 3-bit word from the outside world, we could end up having bit encodings that don't match any of these things. And to preempt that, we need to add constructors for these illegal cases. So which values did we have? So which values can we encode? Well, at 0, so with byte, basically, if we look at the bit level, what values does it encode? Well, 0 and 4. For half, we get 1 and 5, and word encodes 2. So
I'm sorry. Why do we have encoded byte in 2 bits and then using only 1 mask?
So this is the mask for the fields. And this mask is 2 bits wide, so it's bit 1 and bit 0. Does that make so? This is the value of the constructor half, so basically 1. And then we store this value 1 in the 2 least significant bits of the 3. So load store with takes up 3 bits in total, and the constructor bits are stored in the least significant, 2 least significant positions.
Okay. And I'm sorry, what's about the mask?
So the mask indicates which positions the value. So this encodes basically the value of the that we take, and this encodes the position in the inside of the 3 bits where we're going to put that value. And we need to tell that because we're going to put this field bit, the sign, we're going to put that in the most significant bit.
Okay. Okay, I understand.
Right. So there, if you go to Hackage and to and look at the Clash Prelude, there's a, there's more documentation on these data representations, annotations.
Okay, thank you. It makes sense.
Okay, super.
Gregor also asks, corresponding to that, does that mean you can have fields in non-continuous bits?
Yes, you can have non-contiguous masks. Currently, and this is something I discovered whilst working on RISC-V. So RISC-V actually also does, not only are the fields non-contiguous, they're also not ordered from MSB to LSB. And that's something that this data representation currently does not handle. I'll quickly go to the spec, see if I can find it. Right, so the jump instruction encodes the most significant bit of the address at bit 31, and then suddenly bits 10 down to 1, it's stored in bits. So, okay, this is not a case of non-contiguous, but it is an unordered, I guess it is non-contiguous, but it's also not in a, it's not ordered from MSB to LSB. So this is something our current annotation system does not handle. So it can handle non-contiguous, but it doesn't handle unordered. Yeah, well, which makes sense because currently we only say, so you give a mask per field, but within a mask you can't say the order of the bits.
Well, you could have each mask itself be a list of masks where each part corresponds to something in MSB.
Yes, yes, a future version is something, but the current version can't do that. But the future version definitely will. And yes, you will have multiple, you'll get a list of masks basically for.
So for the jump thing, would you currently represent it as like 4 separate fields, like one that is 1 bit wide, one that is 10 bit wide, and so on, and then do the reshuffling?
No, so the way I did that is inside of decode. So here we have this immediate, so this 20-bit immediate field for jump. And I just slice it and concatenate it together. So we don't use the bit encoding annotation for this particular field. That's again because if I go to our instruction data type, where is it? Right. So again, I'll come back to this later. In this case, I use pattern synonyms and a new type wraparound bit vector. So I can't even encode some of product types in this way. And I'll discuss a bit later why I did this. Okay, so coming back to our load store width. So, we can get illegal encodings from, so these are the values, the 3-bit values that are, let's say, legal encodings, but then we have 3, 6, and 7 which are not legal. And we might have to deal with them. So basically what I did here is I created 3 more constructors, illegal 1, 2, and 3. And I gave them their encodings. But then what I did, and people are going, are going to curse me for it, but I export load store with, and I give these 3, and I only export the legal constructors. And this means that you can, if you compile with all warnings and you match on these 3 constructors, GHCi will tell you like, oh, but you haven't matched on all of them. But I didn't export them. So this allows you to either explicitly deal with invalid encodings and do something, or you can say like, well, if it's invalid, then I treat it as a word. Like you pattern match on byte and half, and then if it's a word, then so if it's not byte or half, then it must be a word. So this is what I did for this project. So I created constructors for the illegal encodings, and then just not export them. And then GHCi with warning all will tell me whether I'm handling these illegal encodings properly or not. So now coming back, so I mean, this worked well for for a 3-bit field, and now I'll get back to why I didn't do it for the other one, for the opcode field. That's because it takes 7 bits. And if I wanted to encode all of the illegal states in a sum type or sum of product types, it would take me a long time to, or I might need, like I might have to use template Haskell to generate all of the illegal constructors, basically. So that's why in this case, I just used pattern synonyms to encode these opcodes. And then the way I did it in this case was, again, I just export opcode then with all these pattern synonyms, but I didn't export the constructor for opcode. So GHCi will complain again if I don't, if I just match on all of these and don't have a fall through case with warning all, you will get a warning saying like, well, there's some encodings that you didn't match on. So that will help you. So these are, just 2 things that I want to, like if you're really new to hardware, then this might mean nothing to you, but once you get into it, hopefully you'll remember this part of the talk and like, oh yeah, I remember Christiaan saying something about it. Let me watch this part of the video again. And then you can see. So sometimes, yeah, you don't have, I think so also we can make sure that
also has another question on this illegal patterns. And his question is, what would go wrong if you just don't define line 230 to line 232? I hope that's a correct answer or correct version of his question. And if it's not, he can just chime in and correct me. So if you just don't implement them.
Yes. Okay. So to answer that question, so what happened if I wouldn't encode these illegal instructions? Then you go your merry way and you specify, and you in your circuit you'll say, oh, if it's a byte, then do that. If it's a half, then do that. If it's a word, then do that. And you compile with warning all, and GHCi will tell you, yeah, it's all good. You've matched on all of your constructors. And then some person gives you a malformed instruction, and your circuit does something really weird and it can't recover. And so the generated circuit will behave way differently than what you saw in your, let's say, Haskell simulation, or running your core as a Haskell CPU. And yeah, you might just want to handle these illegal states properly. And again, this is only a problem because we're not in full control over the data types going in and out. Like, let's say if we wrote if we work in, let's say, a closed system, and we would have a compiler that would use, these same data types, it will make sure that, these illegal encodings are never picked. And so we wouldn't have to have these encodings for illegal states. But because we're working in an open system, it's probably better to have these illegal states here. Otherwise, your degenerated Verilog might behave like might behave very differently than especially if you want to differentiate between matching on words and having these illegal states, basically. I hope you. Can I use complete pragmas to pattern match? Suppress pattern match warnings? Maybe. I haven't used them much.
I asked that question in the chat. Maybe the answer comes from the chat.
Yeah.
Oh, sorry. Said this will be answered in the chat.
Okay. So yeah, that's it about some of the, non-Haskell parts of Clash that you might have to think about, bit encodings, or making sure that the generated ports are named correctly. Otherwise, Clash will just do the right thing. It will pick encodings which are suitable. So, anyways, so I'm not going to go. Sadly, I can't go over the rest of the core. You can inspect it. I will keep on updating the tutorial work and maybe turn it into a set of exercises that you can do so that you can actually build it up from scratch. But yeah, we'll also need proper tests. So now coming back to testing. So we've generated, I can generate again. We generated our core. Let me actually open up a different one. I need to run on a different machine because this one has the formal verification tools installed. So we can do cabal run. So we can generate the Verilog. Sometimes the GHCi part takes the longest time. In case of Myrtle AI, definitely Clash is the slow part. Yeah, Clash was designed as a nanopass compiler, which didn't really work well for whole program optimization, at least not the way I take the blame for this, the way I designed it. We're working on and so their compiles can take up to 30 minutes to go from Haskell to Verilog. we have a very smart person on our team, Alex. He's building a partial evaluator, and hopefully we'll get an order of magnitude speed up, so we can get those built down to 3 minutes instead of 30. Regardless, so we've generated our Verilog. We're now going to integrate that into the RISC-V formal. If you follow so I don't expect you to have installed these tools because it was a very late edition. Also wasn't mentioned in tutorial MD. So I'm just going to show you. So this uses the RISC-V formal output, the RISC-V formal interface of our core and like I said, it doesn't bound a model check. It runs it for, well, here you see how many cycles it runs. So it runs the core for 30 cycles. And then inspects the trace that basically the core is outputting on this formal interface, and check that it behaves according to spec. So let's go to cores and then contronomy. Let me copy the relevant files. So we need to copy and of course it would be nice if I could actually integrate the formal tools inside of the test suite of contronomy, but I'll do that at a later date. So we get we want the one with the formal port, formal verification port. So I'm going to copy this one, and we also need to do this one. This one is called slightly different than we currently expect. We need to update that. Now we need to generate the checks that the formal tool should do. So we are going to and this will create all these checks. Now I need to make sure that so this RISC-V formal tool, like I said, it uses symbiosis, and the way that sort of works, so we might get it in Haskell as well. So it at least the way I believe it works, it translates the Verilog to let's say SMV kind of satisfies or SMT style descriptions, and which it then runs the proofs on, I think. But it uses this tool suite from Yosys and Symbiosis, and in this case it uses Bullock there. Let me go back. Right, so I need to make sure that's in my path. And then I can okay, so it's now going to run a formal verification of the core, and it's going to formally verify that the RISC-V instructions that we've implemented behave according to spec, and is going to check that exhaustively because after 20 cycles, the core will definitely be in a state where it has executed the instructions. Actually, one of the checks that it does is this cover check. And here we specify what it does. And it basically says like, oh, if it's basically saying like, if 2 instructions have been retired, then we've done enough cycles. And I forgot what it stands for exactly, but let's say this cover check passes after 15 cycles. So as you can see, all the other ones have more than enough cycles to give a full trace. And so this will be running in the background. You can expect, and you can see, oh, it passes. So we'll just have this run in the background, and we'll go to the Python part of the tutorial. Now, you know, honest to God, this was my first time using Python. So please don't ask me any questions on Python. But it worked well enough. So we're going to, you know, we have generated our Verilog core. We've generated the Verilog for our CPU core, but it's kind of dull because it only has these interfaces to communicate. You know, there's 2 Wishbone buses, one for the instruction, one for data. That's kind of dull, right? We want to interface with the outside world. We want, you know, and have a, for example, communicate over a serial port so we can read it. And you can, you know, send over commands and stuff, or blink lights, or whatever, all kinds of things that you want to do, or add some acceleration peripherals. So this is where LiteX comes in. That's this system on chip builder, which uses a Python embedded domain-specific language called Migen to construct the entire system on chip, but also does all kinds of other stuff under the hood, which makes it really great, which we'll see, or which some of you have already done, because all you had to do was do lxsim, and it would build the entire SoC and would start the simulation in Verilator, and you would have a running system in simulation. So anyways, I can't give you too much details due to time constraints, so I'll just go to the contronomy core. So again, I don't speak Python really well. Anyways, so we defined this class, and the way I did it, I basically looked at the other cores that are defined here. So these are all other, not all of them are RISC-V core. For example, this microwatt core that we see here is a Power 9, IBM Power 9 implementation. And some are open RISC, but a lot of them are RISC-V cores. And here we specify some aspects of it, where I/O should live, whether it's little or big endian. Here we are passing some flags for GHCi, so it compiles correctly. So here we specify that we implement the RV32i instruction set. So explicitly, we do not support hardware multiplication. And then here we set up our system, and so that it can be integrated. And again, this comes, so there's a system-wide reset that we use. There's a system-wide interrupt bus that we use. Then we have the instruction and data bus, which are these Wishbone interfaces. Then our peripheral buses are these 2 buses again, and we have no memory buses. we just use the Wishbone bus. And then here, we specify how the generated Verilog should be integrated into our into the entire system on chip. And so the way this works is that this dictionary, because it's prefixed with I underscore, it will know that this is an input. So it will hook it up to as an input. And if it's an O, it will hook it up as an output. So this is all Python dictionary magic under the hood. So we hook up our external interrupts. We don't hook up the software and timer interrupt. If in case you're wondering what a software interrupt is, this is like if you're in a multi-core system, then one core can send an interrupt to another core. So they're like an async exception, basically. And here we connect our Wishbone buses. Then we call here add sources platform. And if you follow the instructions in the tutorial, I told you to, or I said that we should, you should clone this Python data.contronomy, CPU.contronomy. This contains the generated Verilog for, the Verilog that we generated from our Haskell design. And this makes it easy to integrate it into our design. Like currently, I just copied the Verilog. Perhaps at a later stage, basically this add sources thing can actually run Clash and get the sources automatically. But in this case, it gets these sources from this Python data CPU. And again, as you can see, how did I come up with this? Well, I basically copied it from, in this case, the serve CPU. And then there are some other things. So some CPUs can have their initial, like the start address of the program counter be set. In Gauss case, it's hard coded. So we check that you actually never use this method. And we do some finalization. Here we instantiate our core. And so this allows, so now with this, LiteX knows that our contronomy source code exists, core exists. So I made a mistake in the tutorial.md. I told you to go to LiteX and create the Python environment here. I did that and it didn't really work out for me, the simulation. So instead, what I did was I created it here in the root directory, but then followed the instructions otherwise the same. So if it's not working for you, as it wasn't for me 10 minutes before I started this tutorial, then this is probably why. So you need to create a virtual environment here. So let me just activate the virtual environment. Right, so now I'm in the virtual environment. Because Python is all interpreted and stuff, but I think it would work for Cabal things as well. We can, let's just, this contains, if you look here, this contains our Verilog code. We can just remove that and copy the Verilog. Oh. That we just created. Okay, so I'm really not doing LiteX justice. I thought it was really great that basically the commands that I'm showing you now, that it all just works out of the box. Amazing. So anyway, so I copied the generated Verilog inside this Python data thing so that LiteX can find it. And now if you have Verilator installed as well, we can run, you should have LXSim. You can say which CPU you want. So we want control me. Oh, right. I need to tell it that. And again, you need to set the path after you've entered the Python virtual environment. If you do it before, it doesn't work. Or at least it didn't for me. So it should now be in my path. So if I do LXSim, it builds an entire BIOS that is going to run on the CPU. It builds a simulation, or it should be. Okay, that scrolled by really quickly. So what we have here now is the entire system on chip being simulated using a Verilog simulator. And you're communicating with it over a virtual UART or serial port. And so this just booted the BIOS, and it's reporting all kinds of things. How fast it's running? Well, it's running in simulation, so it's running at 1 megahertz. That we have ROM, that we have SRAM, and that we have a main RAM. And we can ask for help. Again, this is all running now on our core, right? We can ask for help. We can calculate the CRC. We can ask for our identifier. You know, this is now executing. You know, this is not some high-level simulation. This is compiled C code running on a Verilator simulation of our entire system on chip. So this is as close as you're going to get to, let's say, running programs on the RISC-V core as you're going to get without having an FPGA. And so you can play with this. You can make mistakes. If you go too far, you're going to go outside of the available. If we scroll up a bit, it's saying where stuff lives. So SRAM doesn't start until here. So if we access illegal locations, it is going to crash. So if I'm going to ask for the CRC of the first 80,000 bits, you basically got stuck, and the only way to exit is to kill the entire simulation. If I do the same on the FPGA, the only way to get out of it right now is because I didn't hook up a reset pin, is to actually disengage the power and boot it up again. Okay. So unless you have the DE0 Nano FPGA development kit, you won't be able to follow along with what I'm going to show you now. But if you have, and you have it set it up properly, which is unlikely, then yeah, we should actually now build the entire system on chip, run the FPGA tools, which are going to take our Verilog from, you know, the one that we generated from Clash, but also all of the Verilog generated by LiteX for the system on chip, and it's going to turn that into an FPGA configuration. So the way that works is we can do, we can go to LiteX boards, again, LiteX boards, targets, D0 Nano. We can ask for help, and it outputs all kinds of things that how we might want to configure our SoC. But the most important part is that we want to, of course, run our contronomy core. So it builds the SoC. Now it's building, that went really fast. Now it's building the BIOS again. Oh, I of course need to tell it. So I need to tell it not only which, so build tells it to build the actual FPGA bit stream, and I also wanted to load it onto the FPGA. Yeah, it always does this building the BIOS kind of thing. Okay, so now it's starting the FPGA bit stream building. So this is going to build our entire configuration. I'm going to start my serial console. Set it up for the correct speed. And now wait until it gets there.
Can you increase the font size of the terminal?
Yes,
just to be prepared.
I will. So you might be thinking that the FPGA configuration is taking a long time. The work that we're doing, for example, at Myrtle AI, where I'm helping out as well, there the builds can take 4 hours if we're lucky, sometimes 8-hour builds. So the iteration times can be quite abysmal for FPGA design, but that's because it's solving a really hard problem. Okay, so now it's running on the actual FPGA. We can run the same commands again. So we can ask for the CRC. We can tell it to reboot. Like it's doing this mem test. We can ask, I can make the font even larger. Yeah, we can ask for help. The identifier to, oh, as you can see, this corresponds to mostly my local time zone, like it was just built. Can do a mem test. We have to make sure that we we can do all kinds of tests. So yeah, let me see here. We've shown that it can boot and stuff, but of course we're interested in what the formal verification tools think of it. So and as you can see, it passes all of our formal verification tests. There is one caveat to this. So it implements all of the all of the instructions correct. And because of this test bench, I actually got that part of the CPU to work quite quickly. What I didn't check, formally verify, was that I was adhering properly to the Wishbone interface, or the protocol, which basically says like, you know, after a acknowledge has arrived from the slave, you're supposed to deassert the cycle and strobe value for at least one cycle before you assert it again. And I did things like, oh, if there's an interrupt, I will immediately load the new instruction corresponding to the interrupt vector and, you know, skip the execution stage. But this is wrong because, as we saw earlier, right, during our, if we're in the instruction fetch stage, we keep this bus select and bus cycle high. So if I now were to switch suddenly to another location in the program, we're basically now changing the address whilst bus cycle and bus select were high. And that's a violation of the protocol. We have some integration for these formal verification tools. So I think it would be really nice if I could, it's not there yet, but that I can add basically assertions to this Wishbone interface that basically checks formally that it's protocol compliant, as in the core will never enter a state where the cycle and strobe values were asserted, but the address or write data changes. So those are the biggest problems that I had when actually developing the core. And similarly, in the execute stage, I forgot, I did things like the load store unit should not load or store values if it's at an unaligned address, because you can store words, but words need to be stored at 4-byte alignment, and if they're not, then you shouldn't execute it. And there I did things like I detected that, but I already asserted that I wanted to transfer data on the data bus. And then the exception handling unit said, oh, I've entered the trap. Let me switch directly to the instruction fetch stage again to load the trap/interrupt handler. But of course, I had to wait. I shouldn't have started the bus transaction on a data bus to begin with. And so that threw the data bus into a loop, which exemplified in my case by this mem test by just getting stuck right away because I was throwing the bus into a loop.
I think in the formal verification output there was one fail.
Oh, was there?
Just out of interest.
That's bad. Ah, you're right. The liveness check failed. Let me see. Interesting. I hadn't. I hadn't checked that before. Okay, so that means there's still a bug that I need to. I didn't actually run the. So there were, like I said, I had issues with the data bus and the when you had traps and exceptions, and I think I might have messed something up. So this liveness check basically determines that that the core never gets stuck, or at least it makes progress in some way. Yeah. Interesting. I guess it's something they say in the quick start guide for the RISC-V formal verification as well, that you shouldn't just run the verification once and once it passes, you're like, I'm done. You should be running it more often, which I should have for this case. So apparently there is the core can enter a state where it gets stuck, and I would have to investigate which one that is. So, right, to conclude, so we've created a RISC-V CPU in Haskell. We used Clash to convert the Haskell description to Verilog. We've formally verified, caveat one failure, we formally verified that it is mostly correct, except for the liveness issue. And have done that so exhaustively. We've integrated the generated Verilog inside a larger system on chip, which, as you can see here, it includes SD-RAM. It contains a UART, and you can build so much more inside of this system on chip builder called LiteX. Right, so we integrated the generated Verilog into that. Then we told LiteX to build our entire system on chip, which we could run, a simulation, a Verilog simulation of our entire system on chip on our PC. And I could also use LiteX again to build the entire FPGA configuration and have our RISC-V core written in Haskell, running on an actual FPGA and being able to communicate with it over a serial bus. I want to thank you all for your attention and staying with me through this alpha run. I have no idea how I would ever be able to fit everything I wanted to discuss in 2.5 hours. I think it's simply impossible. But it's given me some ideas to at least turn it into a 2-day workshop where people can do exercises and build the course themselves. I think there isn't too much guidance. I will update the tutorial.txt. So let's say if you come back next week, this tutorial text will be updated, and then you can slowly build the CPU core bit by bit until you have a working system and build entirely yourself. And you can always cheat by looking at the next slide if you think you're stuck. Thank you again for your attention. If there's any questions,
thank you for your workshop. Yeah, I think we have some questions that were already collected in the chat. Maybe Gergo, if you want to start with one of your questions.
Well, yeah. So one of my questions was, given that Clash is higher level than Verilog, for example, you have memory there. Is it possible that you could make a more efficient representation as an SMT problem of the circuit's behavior than going via HDL and then these off-the-shelf tools? Like, is it possible that Clash could directly generate SMT problems which would be easier to solve?
You mean assembly programs to run on the RISC-V core, or?
Sorry, not assembly, SMT.
Oh, you mean whether it would be possible to, let's say, formally verify the Haskell code directly in a way, as in generate SMT from Haskell?
Exactly. Like basically some SBV like thing.
Most likely.
I mean, the question is not so much if it would be possible, because I'm sure it would be possible. The question is whether you think that there's some efficiency to be gained from understanding more of the circuits than at the HDL level.
But the feedback will be better. Currently, like I can show you that. So we're always improving this.
Oh, I think I see what you're gonna show me. You're gonna basically tell me that currently you get 1 bit of output from the formal verification, whereas if you generate it from Clash, you could get meaningful failures.
Yeah, you get meaningful errors basically, or you get meaning, like it's saying like, oh, this line in the Haskell code, instead of basically having to inspect the generate. Like now the tool will complain about the generated Verilog, and then you sort of have to hopefully figure out how that translates back to your Haskell. So yeah, in terms of errors or interpreting, in debug cycle, basically, it would definitely be an improvement. If that answers your question. Then your question.
This is a different avenue, because I was just thinking about the performance, but you're right that the fact that it would be closer to the original source would also mean that you can map back the failures easily, so that could be interesting.
Yeah, I mean the performance wasn't that bad, right? I mean, like the longest check took 10 minutes, but all the other checks, like they finished under a minute. Like, yeah, perhaps if it wasn't generated Verilog, but it would have been done faster. Yeah, but I guess at some point, like if it's in CI or stuff, it starts to matter how long it takes. And then if you can generate a way smaller SMT model, that can probably be verified faster.
Okay.
Yeah, then the question.
Yeah, do we have other questions? Yeah, I want to say the same.
Yeah, I saw that another question by Gergo. Is Verilator used just to simulate the CPU? No, the entire SoC is generated. It generates Verilog for the entire system on chip, I believe.
You can also ask your questions directly to the chat if you want, if you have any.
Yeah, I'm going by. That's another. How well does it work if the core is not a GHCi target? I don't know. This is my first foray into LiteX, and like I guess to people who are not in the embedded hardware space, it might seem all natural to what just happened on screen. But let me tell you, it's definitely not. That it works so out of the box by somebody who's never used it, like me, like Python noob. It was awesome. I guess the do you have the Python CPU contronomy? I think that was already answered. Can it be used with an Intel 880 core? I think so. Like I said, if I go to LiteX, let me open the correct editor. So Vex RISC, Serve, Rocket, Pico, RV2, they are all RISC-V cores. Then more 1KX is a open RISC. Minerva is another RISC-V. Microwatt is a Power 9 implementation. LM32 is some other thing. I forgot which instruction set it is. So let me just look at the microwatt thing, for example, because that answers the question perhaps best. I should look in here. SoC, cores, CPU, microwatt. Oh, right. Yeah, so apparently here they specify PowerPC little endian, and I guess it then works. You would have to.
Yeah, but
maybe
I guess
listen.
my question is more like, you said that it has all these SDRAM cores and UART and so much more. But I'm interested in whether it can do so much less, because these are all somewhat contemporary cores. They have these elaborate I/O buses that they connect to and so on. And I was just thinking that whether I could use this to replace the simple old school circuitry that I sometimes need around old CPUs just to make them do something. Just yesterday I had to write, I don't know, like 30 lines of Haskell code just to hook up an Intel 8080 to run Tiny Basic on it, because then you need some memory, you need UART or something to communicate with the outside world. And I'm just thinking whether I could not have to write any of that and just pop in the core into this one and put a static RAM and some UART done with it. But this is like, so basically I guess what I'm asking is whether I can go back 40 years and use it on 40-year-old technology.
I think in practice the answer is no, because you just have to write so much then inside of this LiteX framework. I think like the way it helps you now, like if there's already all these kinds of peripherals, but what's nice is that there's a single Wishbone bus, and you can say, oh, add this peripheral at this address and add this peripheral at the other address, and it will create the master or the Wishbone switch automatically based on those addresses and those kind of things. And I'm not really, so it really helps there. I think if you want to go to these old school things, you'll have to implement a lot yourself still. But if you, let's say, maybe it would be sufficient just to write a old school to Wishbone interface, and then you could go from there, because I think maybe, was it the Pico RV32 one? Yeah, I don't know. You would have to look, but there might be some. No, I think these are all, they are all either Wishbone or XE4 buses that they use here, not something older than that. Yeah, like I said, this was my first foray into LiteX. But it's a super active community, so if you go on their IRC, they'll probably be very helpful.
Okay, wonderful workshop. I think we are at the end of our time slot.
Yes.
So just thank you again. It was very impressive, and I think also the feedback was already very positive. And I think you will answer further questions in the chat, right? And
yes.
Okay.
Yeah.
So if something immediate or some important questions pop up, or if some help is necessary, I think the chat will still be helpful. And have a nice day. I think the next slot of talks will start in half an hour. So see you then, and bye.
Right.
Thank you.
See ya, everyone.
Thanks for the workshop.